Let's now talk about big O notation. As we have discussed earlier, big O notation is used to represent exact or upper bound on order of growth. Please note that if you know the exact bound, you would prefer to use theta notation. That gives you more information. This is what exact bound is. So main use of big O notation is when you want to represent an upper bound, right? When you have an upper bound, you use big O notation to represent the upper bound. So there is a direct way of finding the big O notation for an expression, and the direct way is just to find the order of growth, and since exact is there in big O, you write the order of growth in big O notation. So these are the steps that we use to find the order of growth also. So if you see this expression, the order of growth is clearly n square. We ignore the lower order terms, we ignore the leading constant, and we get the order of growth is n square. And since big O notation covers exact or has upper bound, we can write it as big O of n square, right? Mathematically, you can write it as big O of n cube also, n4 also, anything higher, because big O of something means that thing is order of growth wise greater or equal, right? So we are writing equal here. When we know that's equal, why to write it upper bound, right? Why to write a higher value? So in this expression, this is a lower order term because we have n log n here, right? N log n is a higher order term. We ignore the lower order terms, we ignore the leading constant, so we have the order of growth as big O of n log n, right? Let's now see this expression. Here we ignore the lower order terms, we ignore the leading constant, and we have order of growth as big O of n cube. So this is a direct way of finding order of growth. Now you see mathematical representation of big O notation. How do we mathematically see big O notation? Let's now talk about mathematical definition of big O notation. Please remember one thing, whenever we talk about asymptotic analysis, asymptotic notations, we talk about values of n tends to infinite, large values of n. And that's what you would notice in this definition also. We have n greater than equal to n naught. So we are talking about all the values greater than a certain constant value n naught. For those values, this condition should be true. Fn should be smaller than or equal to C of Gn. Then we say Fn is big O of Gn, right? So for example, if you have Fn is 2n plus 3, you would say it's big O of n. So what is Gn here? Gn is n, right? You would say it's big O of n only when there exists a constant C such that 2n plus 3 is smaller than or equal to Cn for all n greater than or equal to n naught. We just need to figure out these two values, C and n naught, and we need to show this thing. Then we can say this is equal to big O of n. And we have learned in the direct way that we have this as big O of n, right? We can ignore the lower order terms, we can ignore the leading constant, we can quickly say it's big O of n. Here the intention is to just to show you mathematically also, right? How does this work? So we have Gn as n and we have Fn as 2n plus 3. Now we need to find out two values, C and n naught, and we need to show that this is always true after values of n greater than or equal to n naught. For that purpose, I have taken C as 3. Now you might be having a question, how did I pick 3? See, what you can do is, you can always take the constant of the highest growing term, which is n here, right? And just add 1 to it, right? To prove that this is big O of n, you just add 1 to it. So now you get 3, right? So your C is 3, and you need to show that 2n plus 3 is more than or equal to 3n for all values of n greater than certain value. And that certain value can be figured out by just simplifying the inequality. We have 3 is smaller than or equal to n now. So n naught becomes 3. N naught is 3 and C is also 3, right? You can notice that after value 3, this value 3n is either greater or equal. See, if you see 3 itself, they are same at 3. This is 6 plus 3, 9. This is 9. Now if you take 4, this is 4 into 2, 8 plus 3, 11, and this is 12, right? For all the higher values, this term is going to be greater. See, why does this work that we always take just one higher value? Because it's the higher growing term, right? This is the highest growing term among all the terms. We have two terms here and it's the highest growing term. So if you keep on increasing the value of n, it will dominate over other terms. And if you have a higher multiplier, this is definitely going to give you higher values after certain value. Let's now see more examples of big O notation. So here I have written constant values. Any constant value can be written as big O of 1. For example, 100, log 2000, 10 to the power 4, 10 to the power 8, 10 to the power 10. All these are big O of 1. As long as the value is not dependent upon n, there is no n in the term, we can write these values as big O of 1. Here are examples of big O of n. And please note that I have U here. U means union. See, big O notation means exact order of growth or higher order of growth. So we can cover these terms also. These both terms come under big O of n, right? So constant also can be written as big O of n, but ideally you would not write them as big O of n. You would write them as big O of 1. When you know that it's exact constant growth, you would write big O of 1 notation. And in fact, you would not use big O notation for those purposes. You would use theta notation, right? Ideally, you would use theta notation when you know the exact order of growth. So here are examples: n by 4, 2n plus 3. If you ignore the lower order term, ignore the leading term constant, you will get these order of growth as big O of n, right? Now this is a lower growing term. This is log n, and log n is smaller growth than n. Still we can write it as big O of n, but ideally we would write it as big O of log n, or even better would be theta log n. When we know exact order of growth, we would write using theta notation, not big O notation. These are just to explain you mathematically. So let's see this example. In this series, we have all the terms that have order of growth of as n square, and we can write all of these as big O of n square. And we can write these also as big O of n square. But again, ideally, you would like to write the exact order of growth. You would like to write this as big O of n or theta of n. This as theta of log n or big O of log n. Big O notation works for multiple input variables also. For example, if you have 100 n square plus 1000 m and n are two input variables, what we do in this case, we again take the highest growing terms. So n square is the highest growing term. Then for m, this m is the highest growing term. So we write n square plus m as the order of growth. Let's see this example. M square is the highest growing term for m, right? For n, we have two terms, n and mn, and mn is obviously the higher growing term, right? It's multiplied with an input variable. We talk about m tends to infinite, n tends to infinite. So we have m square plus mn as order of growth of this expression. Let's now talk about applications of big O notation. Please remember one thing. Whenever we have exact bound, whenever we know the exact bound on order of growth, we should prefer to use theta notation. Why to use a notation which gives you a loose information? Say if you have an algorithm like finding maximum in an array, right? You know that whatever input you provide, you are going to traverse through the whole array, right? And you are going to find the maximum by traversing through the whole array. So it's always going to take n order of growth. So why to use big O notation? Why to say big O of n? You can better say it's theta n algorithm to find the maximum in an array or minimum in an array. But many times you have complex logics, right? When you are implementing algorithms or when you are writing some business logic, you have complex inputs which has many if-else conditions, many termination conditions. In those cases, what you do is you try to figure out the innermost statement, the statement which is being executed maximum number of times. You find an order of growth on the number of times the statement is being executed, and then you say that's the order of growth of this algorithm in terms of big O. Basically, you consider the worst case of the algorithm, right? And in the worst case, you find the order of growth and you put it in big O notation, and then you say this is the time complexity. So you have put an upper bound. It's easy for you to get an upper bound many times rather than knowing the exact bound. Let's take an example to get an idea. Here is an example of a function that checks whether a number is prime or not. So the syntax that I have written here, it's close to C, C++ and Java. The only difference in Java is you will use boolean instead of bool. So this function, what it does, it checks whether a number is prime or not, and we are going to discuss detailed working of this function in the mathematical track where we have discussed prime number checking video, right? We are going to discuss in detail how this function actually works. The idea here is to understand an application of big O notation with the example of this function. See what this function does, it checks whether n is 1 or n is 2 or n is 3. These are the corner cases. If n is 1, it returns false. 1 is not a prime number. If n is 2 or 3, then it returns true. They are prime numbers. Now it again has one optimization. If n is a multiple of 2 or n is a multiple of 3, then also it immediately returns false. So if you provide a number like 100, 200, 500, which is an even number, it will immediately return, right? Or if you provide a number which is a multiple of 3, then also it will immediately return, right? It would not go inside the loop. For other numbers, it will go inside the loop and it will go till square root of n. We have the condition I into I is more than equal to n, which means I is more than equal to square root of n. We'll discuss this logic in detail in the prime number video. And what we are doing I equal to I plus 6. So what is happening here? There might be many situations where we do not run till square root of n. For example, if you talk about the number 65, right? Square root of 65 is going to be above than 8, right? Something beyond 8, right? 8 into 8 is 64. Now, but what will happen here? In the first iteration itself, you will return false because 65 is a multiple of 5. So you're taking constant time. But in the worst case, when your input number is a square of a prime number, in those cases, this will run till square root of n, right? So you are going to run a square root of n minus 5 divided by 6 times kind of thing, right? Because it begins with 5, then goes till square root of n and then increments by 6. But we can ignore the constants, we can ignore the lower order terms, and we can say it's a square root of n order of growth, right? That's what we can say. Now, square root of n is not always taken. It's taken only when your input is a square of a prime number. For example, 49. It's a square of 7. In only those cases, you will have this loop running a square root of n times. So what do we say about the order of growth of this function? There are many corner cases where it stops well before a square root of n, right? So we can use big O notation in such situations. We can say the time complexity of this algorithm is big O of square root of n. That covers everything, right? When you say square root of n and when you use big O notation, it means it is either square root of n or less than square root of n. That covers the constant, that covers divisible by 2 cases, divisible by 3 cases, that covers even the cases when numbers like 65 are provided. So big O notation is useful when you have an upper bound. It's also useful when you have a complex logic and you don't know exact upper bound also, but you can approximate the upper bound by ignoring certain things. We'll discuss as examples when we'll talk about recursion analysis. But the idea is big O notation, whenever you don't know the exact bound, you can somehow figure out the upper bound, you use big O notation for those purposes. Also, in general, what you do is you have an algorithm, you find the worst case, you find the order of growth in the worst case, and you put it in big O notation and you say this is the time complexity of this algorithm.